Okay, today we're going to be continuing our learning about a derivative, and we're going to continue to use the standard definition of a derivative until we learn some shorter ways as to how to evaluate the slope of a curve at any point on that curve. So the derivative is denoted by this symbol f prime or apostrophe f prime of x, and it is the limit as h approaches 0, f of x plus h minus f of x over h. And if you want to know how they came up with this formula, you can watch another video on my website. If you're looking for the slope at a specific point on the curve, in other words, you know the x value that you're trying to evaluate the slope, you can actually use what's called the alternate definition, which is f prime of a is equal to the limit as x approaches a, f of x minus f of a over x minus a. Note the difference between these formulas. Here on the bottom we have an h. Here on the bottom we have x minus a. Here the limit as h approaches 0 all the time. Here it's as x approaches a. So pay attention to which formula that you're using. Other ways to denote the derivative are dy dx, from which they've got change in y over change in x, and they basically just converted that to dy dx. The difference in y over the difference in x, y prime, or df dx. This one is probably the least common way of seeing a derivative denoted. So let's see how this works on some sample problems. All right, so we have three functions here that we need to take the derivative of using the standard definition. So let's go ahead and jump in and get started here. The limit as h approaches 0, and we're going to plug x plus h into this formula, cubed minus f of x over h. Now, if you cube this, x plus h times x plus h times x plus h 3 times, you will get x cubed plus 3x squared h plus 3x h squared plus h cubed, still minus x cubed. I'm going through that quickly because I trust that you can do that on your own. And then divided by h, we still have the limit as h approaches 0. So every time you do this, as you know from a previous video, all the terms that do not have an h are going to cancel. And that's going to leave you with a bunch of terms that you can factor out an h. So I'm going to factor out this h on the top, and that's going to give us 3x squared plus 3xh plus h squared over h. And then we're going to cancel the h's out. And then we're going to plug in 0 for our h. That's going to take that term away. That's going to take that term away. And we are left with f prime of x, our derivative or our slope of a function at any point x, 3x squared. And that is how you use the standard definition of a derivative. All right, let's see if we can apply that same concept to this one. All right, so we're going to have, and I'm going to leave off for purposes of space, limit as h approaches 0 till the end. So we're going to have 1 over x plus h plus 3 minus 1 over x plus 3. So here's our f of x plus h minus f of x over h. Now we got to get a common denominator here. So we're going to multiply top and bottom by x plus h plus 3, x plus h plus 3, and then top and bottom here by x plus 3 and x plus 3. All right, let's see what we get when we group all those together. We get x plus 3. And this minus, you have to distribute to all three of these terms. That's very important. So you get minus x minus h minus 3. And all of that is over the common denominator of x plus 3 and x plus h plus 3. All right, and as we said before, all terms that do not have an h are going to cancel. So negative 3, positive 3, negative x, positive x. That's going to leave us with this negative h and that is all still divided by h. And you can flip and multiply, and you can see that this h is going to cancel with this, because all we're going to do is multiply by 1 over h, which is the same as dividing this by h. Let's get rid of that. And so then now the h's are going to cancel, and we are left with negative 1 over x plus 3, x plus h plus 3. And now I'll bring in the limit as h approaches 0. Slap 0 in there for h, and we are left with f prime of x equals negative 1 over x plus 3 squared, because when you get rid of the h, there's two x plus 3's down here, and there is your derivative. All right, we got a lot of space for this one. Let's see if we can work this one out. All right, we're going to plug in x plus h. So it's going to be square root of x plus h minus 2 minus f of x, which is just that, all of that over h. So we've seen these type of problems before. We need to use the conjugate method. So we're going to multiply by x plus h minus 2 plus square root of x minus 2. And we're going to do that top and bottom. So square root of x plus h, and we extend that a little bit, minus 2 plus square root of x minus 2. All right, when we do that, when we FOIL this, the root times the root is going to give us x plus h minus 2. And then this negative root and that positive root are going to get rid of the root, and that's going to leave us with negative parentheses x minus 2. You know what? I'm going to just go ahead and distribute that negative. So it's going to be negative x plus 2. Has to be plus 2 because this must cancel with that, and this must cancel with that. And so we are left with h on the top over h, and then this long conjugate that we multiplied by just a moment ago. Oops, let me go ahead and write that a little neater. And then, of course, as we always see, the h's cancel. And then I'm going to take the limit as h approaches 0. Throw that thing in there. And we are left with 1 over 2 root x minus 2. And that is your f prime of x. All right, in example 2, we are trying to find the slope of this curve at a specific point. So let's go ahead and draw this curve out so you can visualize exactly what we're trying to do here. So we have our xy axis, and we have the square root curve, which looks like that. And so let's say we have the point 9, 3 right there. So 9, 3. We are trying to find the slope of the tangent line that touches that curve. So we're trying to find the slope specifically at 9, 3. So let's see if we can do that. Since we know the point, we can use the alternate definition, which is the limit as x approaches a, f of x minus f of a over x minus a. And I think you'll find that this formula is a lot easier to use than the other one if you have a point. You can only use it if you have a specific point. So let's go ahead and do that. F of x is root x, so we'll do limit as x approaches 9. Okay, so we're going to now make that 9. So f of x is root x minus f of 9. Square root of 9 is 3. And then that is going to be over x minus 9. So now we can multiply by the conjugate. And so let's go ahead and multiply top and bottom by root x plus 3 and root x plus 3 here. When we do that on the top, of course, you've seen this before, you're going to get x minus 9. And whatever you do, do not multiply this on the bottom, because you want to recognize that you can cancel off the x minus 9s. So let's go ahead and cancel those off. So x minus 9 is gone. And then we are going to take the limit. Now this time, not as h approaches 0, but as x approaches 9. So you're going to have 1 over the square root of 9. So let me write this out. Root x plus 3. So now the 9 goes there. So root 9 is 3, so it's going to be 1/6. That is your slope. Okay, part B is a problem that you do not need the alternate definition of a derivative for. Matter of fact, anytime you have an absolute value function, you don't use any of the definitions because most of these problems are simply, you're simply finding the slope at a specific point. So this is an absolute value function and it's shifted left 1 unit. So it's just basically going to look like this. So the nice thing about an absolute value is if you're on this part of the curve, the slope is positive 1 at any point. And if you're on this part of the curve, the slope is negative 1 at any point. So, well, you're actually trying to find the slope at negative 1. So if it was any point other than negative 1, then you would say, oh, the slope or the derivative is 1 or negative 1. But here, it's actually at this corner, and we'll learn on another video that the derivative does not exist at a corner. Let's go ahead and work this out using the alternate definition. So we'll say the limit as x approaches negative 1, and we will put f of x, so absolute value of x plus 1, and then f of negative 1, well, negative 1 plus 1 is 0, so that's just going to be minus 0 over x plus 1. And so what do we notice here? We notice that when we plug in negative 1 into our derivative, we get 0 over 0. We also recognize that this derivative is going to look like this. It's going to look like 1, and then at negative 1, it's going to jump down to negative 1. So it's going to be one of those type of graphs. So the derivative, because the limits are approaching different numbers, the derivative at negative 1 does not exist. So you'll write does not exist because we got 0 over 0, and you have two totally different slopes, and so the slope at this corner is going to be non-existent. Okay, here we have a graph of a function, and it looks like a cubing function of some sort, but we don't know for sure. And we have the slope at various points on this curve identified. So at point A, the slope is 4. At point B, the slope is 1, so on and so forth. And it wants us to graph the derivative of this function using the information that we have. So let's see if we can go ahead and do that. We're going to graph it on the same graph. So at point A, if you draw a tangent line, the slope is 4. So I'm going to put a point at 4. And then at B, we see that if we were to draw a tangent line, it looks like the slope is about 1. So I'm going to go down here and put a point at 1. So let's go ahead and put a point there. And then at C, we have a horizontal tangent. We know that the slope of any horizontal line is going to be 0. So I'm going to go ahead and put a point at 0. And then at D, here we have a negative tangent line with negative slope. So I'm going to go down and I'm going to put this point right there. And then at 4, we don't really know what the slope is, but at 5, we know the slope is negative 1. So I'm going to put a point there. So probably we have another point there. And then at 6, we have a slope of 0. So that means I'm going to go to 0, put a point. And if I were to connect all of this, all right, it looks through here, comes down there, and there we have it. So we can see that if this is a cubing function, looks like the derivative is 1 degree less. It's a squaring function. And we'll learn that when we learn the power rule. Example 4, we want to sketch the graph of a function that has the following properties. F of 0 equals 0. So let's go ahead and draw our xy axis. And it says f of 0 equals 0. So let's go ahead and put that point on our graph. So we know that it has to either touch there or go through there. Then it says the graph of f prime, the derivative, is shown to the right. So this is our derivative. And so essentially what this is saying is that from 1 backwards, from x equals 1 backwards, the slope is constant at a -1. And then right at 1, it switches and goes to a slope of 2. All right, so let's see if we can draw this. So we know that from 1 backwards, it's going to have a slope of -1. So maybe we'll draw this line. We'll make it go like this. And then after that, it switches to a slope of 2, which is a little steeper. So we will make that the slope of 2. So a slope of -1 and a slope of 2 constant. And at 1 is where the slope changes, and it goes through f of 0, and it is continuous for all x. So our graph matches the qualifications. Okay, we're going to finish our lesson today by talking about one-sided derivatives. And we're going to learn in our lesson on 3.2 differentiability that in order for the derivative to exist at a certain point, the derivative must be equal from both sides. In other words, the slopes must be approaching the same value from both sides of that point. If not, then the function is not differentiable at that point. So let's see if we can just graph this by hand, since it's a pretty simple piecewise function. To the left of 0, it looks like a parabola. So we'll just draw a basic parabola there. And then to the right of 0, it looks like a linear function. So with a slope of 2. So there we have it. Now you can clearly see that right here, there is a sharp corner. Right here, there's a sharp corner right here. Anytime you have a sharp corner, that means that the derivative is not going to exist there, because the slope from this direction is 2, and the slope here is approaching 0, as we're going to see. So therefore, when the slopes are not approaching the same value, the function is not differentiable. But let's actually prove that algebraically. So we need to find the slope of this left-hand function. So we're going to take the limit as h approaches. Actually, you know what? We can use the alternate definition, because we are trying to find the slope at a specific point. So we can say as x approaches 0, f of x, which is x squared, minus f of a. So you're going to plug 0 in. That's just going to give you 0. So remember the alternate definition, over x minus a, or x minus 0. So we simplify that to x squared over x, which is just x, and then we plug in our limit, and we see that it ends up giving us 0. So let's say f prime of 0 is 0. In other words, the slope of this parabola at 0 is 0. That makes sense, because if the parabola were to continue, you would be drawing a horizontal tangent line to the vertex of this parabola, and of course the slope would be 0. Now let's go ahead and do the same exercise for the other one. So the limit as x approaches 0 of f of x, which is 2x, minus f of 0, plug 0 into the 2x function, you get 0, over x minus 0. Alternate definition of a derivative. So the x's cancel and you're left with 2. There is no x to plug anything into, so the slope is constantly 2. We know that from the graph. So f prime of 0 is 2. And this slope does not equal that slope. Therefore, you can just say f prime. And when we say this is from the, let's just say this is from the left and this is from the right. So when the two slopes do not equal each other, then you'll say the derivative at that point does not exist.